Mobile bimanual systems work beyond arm's reach, from fine manipulation to large pick and place, in settings like power lines, clean rooms, farms, and warehouses. Originally designed for agriculture, we developed a bimanual cable-traversing robot for harvesting and manipulation, featuring an expandable workspace on a shared, floating cable system. In this work, we explore how variable shoulder distance helps the system carry objects of different sizes and handle tasks more efficiently. The first task is raspberry harvesting. Teleoperation used a physical replica of raspberry to simulate real motions. We tested different shoulder widths and found similar harvesting times, with interference and reachability being the main concerns. The next task, tying a knot, was more challenging, needing twisting and coordination in a tight space. A narrower shoulder width didn't help, despite better overlap and orientation. Still, the task was doable within 70 to 100 seconds, until the arms were too far apart to share workspace. Another simpler dexterous task was tested, using a tape roll. The operator had to rotate it to the right angle, then precisely grasp and pull the tape tip. When the arms were too close, collisions were frequent, and the narrow shoulder width limited usable workspace, requiring more fine adjustments. In contrast, a wider shoulder width allowed smoother, more natural motion. We tested more tasks with different fixed shoulder widths, including tearing paper, picking up a pole or pen, and opening then closing a pen. All tasks were successfully completed. However, dexterous tasks took more time than simple pick and place, which only requires the object to be within reach. For manipulation tasks, performance depended more on shoulder width. Since the robot arms have human-like proportions and the tasks mimic daily actions, the fastest performance occurred when the shoulder width was close to that of a human. In most applications, two single arms with independent mobility are more flexible than dual arms sharing the same base. To simulate a dual-arm robot with a shared mobile base, we mounted both arms on a board, fixing their distance at 0.385 meters. In agriculture, for example, harvesting often requires only one arm. The bimanual system allows each arm to work independently most of the time and join only when needed, such as to remove blocking leaves. In our task demonstration, variable shoulder width enabled faster harvesting by supporting this individual operation mode. This setup improves efficiency by reducing idle time, where one arm would otherwise wait for the other. Other tasks using the same setup were also tested. First, picking up flexible objects. Variable shoulder width clearly helped with picking up loops and applying proper tension, while a fixed width made the pickup gesture more difficult. Next, an assembly task involved collecting components from different locations and assembling them at the center. For small parts requiring precise, sequential actions in a shared space, maintaining a fixed shoulder width with mobility proved more effective than using the extended mode. Finally, a rope extension task required keeping the rope off the ground, simulating in-air manipulation. These tasks not only demonstrate the benefits of variable shoulder width, but also highlight the potential of cable-traversing bimanual robotic arms in a variety of teleoperated applications.